Com, 100% listener-supported radio, and now we return you to your host.
Hey, welcome back to David Mackey's Shiny Side Out. This is the second hour of our show numbered 518.
8, 10, and 500.
Just remember, freedomslips.com, or as you know it, revolution.radio, is the number one listener-supported talk radio on the net. So push the donut button or subscribe to the archives for free.
That sounded like you said push the donut button. That's hilarious. I want to push the donut button.
Sprinkles.
No, I said it first.
I want the donut button.
That's nice.
Actually, no, I'm back to my keto, so I don't want donuts. Thank you very much. So get yourself some great merchandise from the station's website, and they do have t-shirts, hats, mugs, and a whole bunch of apparel. And you can choose the thing you like with the pattern you like, and then you can change the product that it's on, and you can buy anything you want with Freedom Slips on it, and it's really cool. And the artwork was all done by A Mad Painter. He's one of the hosts. Yeah, it's awesome.
Yeah.
Which reminds me, Macca, we haven't got our t-shirts, but I'll chase that up. I just remembered. And
yes.
I know, right?
What happened there?
Well, it's probably 6 months in shipping. You know how it is these days. Crazy, just crazy. I think with the international visitors returning back to Australia, we'll see our shipping times, going back to regular, because all of the backhaul transit was done with goods.
Yeah.
So hopefully, fingers crossed, that happens. So thanks for listening to Revolution Radio. I really have to say that, because it is listener funded, like I said, but it's an extraordinary experience. There's so many different hosts, diversity of information, diversity of hosts and backgrounds. And, thanks for being with us, to be honest. Now, this topic, Mackie, is one of my favorites.
I know. And the funny thing is this, we haven't spoken about this. Oh, sorry, as a unique topic.
Yes, that's right.
Singular topic.
Yeah, it's been part of the hypothesis topics, yeah.
100%. But as an actual show cycle, not since
2012?
Show 20.
Goodness
show
me.
20. Show 20. Yeah, that was in 2000. In fact, I saved the file August 10, 2012 at 11:55 p.m. That's when I saved the file.
Wow.
There you go. What? How did that happen? That's just crazy talk now. But yeah, no.
Well, guess what that topic is? Ancient aliens.
Correct. Now, important to understand something here. Very important. It is a. I guess it's a highly controversial topic, but I wanted to approach it from a rational point of view, purely scientific, and how can I put this best? Reasonable. That's it. I'm looking at it most reasonably, because the thing is this: a lot of people they just shut off as soon as you mention it, right? Like, no, I don't want to hear it. This is like an automatic reaction. Right, as soon as you start talking about, UFOs had the same kind of reaction. Some people still does, because they haven't caught on to the Tic Tac disclosure quite yet. But it's okay. It'll it takes time to
get into the. And now serious documentaries are being made by the mainstream.
Yes, correct. All
the X60 Minutes lady is now doing, talking about aliens.
Yeah, and that was on occasion by the and it was disclosure by the U.S. Navy.
That's right.
The Tic Tac incident was a real thing.
Kind of let them into it.
Yeah. Now this is really awesome if you think about it. Now, but when you talk about, let's talk about extraterrestrial life. So life that is ultimately not of this planet, right? Or life that may be off this planet but has made it to the stars and is now living on other planets or in space or whatever, but essentially a space-faring community, let's call it, okay?
Yeah.
Space-faring community.
I'll go with that.
Of either biologically very distinct creatures from us, or biologically similar, depending on where they originated from. But let's just talk about that for a second, right? So in order to fully appreciate and approach the subject as clear-headed as possible, there are a number of things we need to look at. Number one, we need to look at the size of the universe, at least as we understand it. Okay. Number two, we have to look at the age of the universe, at least as far as we know, right? And then also we need to understand, well, how many Earth-like planets are there? Now, I'm not saying that all life needs to be like our life, but again,
that would be
simplest
anthropomorphic.
common denominator, right? Just in order to shut everybody up, right? The simplest common denominator. Because I'm not going to argue that that life doesn't need to be carbon-based. Life doesn't. In fact, we know that life doesn't need to be carbon-based.
It could be
we
silicon-based.
It doesn't. Yeah, it doesn't. It doesn't need iron to transport oxygen through the blood, or it doesn't even have to have blood. But my point is, let's just keep it as simple as possible for our discussion here, right?
Because octopus have copper blood.
Yeah, and then exactly, and then blue, and anything blue, like same with a crab. Like if you look at crabs, they have blue blood, right? So, and then once we've figured out how many Earth-like planets there are, let's look at the 10, or I've got the 10 most Earth-like exoplanets here, and let's look how far away they are from us. Let's look at that. So once we've looked at all of that, right, then we can have a meaningful discussion around the probabilities of something like an ancient extraterrestrial visitor, for instance, right? Now, I think there are a number of different explanations possible as to what happened in ancient times. And then we're going to go look at some of the evidence that presents itself, which just doesn't fit the official narrative. And we've talked about that at length, ad nauseum. It's part of the hypothesis, but I really want to give this a serious treatment. And
all right.
I don't know.
Yeah. And at this point in the sentence, I think in the context with it, I think there's 2 points. One, the Drake equation, which we'll no doubt get to, and the other is an example that Elon Musk gave with conventional rocketry that we have today, that it would take 1 million years, only 1 million years, to populate most of the our galaxy, just our galaxy alone, not the universe. In 1 million years, we could do it, but given that it's been around for a very long time, in the billions of years, it's quite possible that there have been a lot of alien species who have done the same thing. We could potentially, as humans, could be just one of those seeded planets from another race, and that's why all the references in the Bible talk about us being made in their image. I think it's an extraordinary place to go, but back to you, Mackie.
Yeah, and again, Dave is right. It's not just the Bible. I mean, look at any ancient creation myth.
Oh, yes.
You find references to us having been. But the funny thing is this: the more ancient the creation myth, the more specific it is.
Isn't it crazy?
The more detailed, right? The more.
That's right.
And in fact, it doesn't read like a myth at all. It reads like something that could have happened to regular folk.
Mm-hmm.
And this is something we need to understand here as well, right? I believe the human race is far older than scientists will have us believe today. And eventually they'll come around to my way of thinking. I also believe that the human race, species, is far more, or was far more diverse than we give it credit. Now, we're slowly getting to the point where we understand that we have a lot of half-brothers and half-sisters, which we can interbreed with, right? We know this. Now, in fact, they recently found, sorry to divert for a second, they recently found the offspring of a Neanderthal and Denisovian. Mm-hmm. So those two interbred as well. So this is just one big family.
That was a party and a half.
There was a party and a half. Now, so it is hard to understand big numbers. I get it, right? And this is why people usually close off and say, I don't want to hear it. But it is really, 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 really important to understand some of these basic facts, at least as far as we know. I mean, we learn more, sure.
And the numbers are so large that it's difficult for our brain to actually imagine the size. So just know them as numbers, okay?
Yeah, and we've put something here together that will hopefully put it into a better context and make it a little bit more understandable. Because people always say, oh, why would they come here? And the universe is so big, and it's highly unlikely that anybody would ever come here, etc., etc., etc. Now, we don't know, number one, what the motivations of people are. We don't know what the level of technology is. Now, one thing we do know, Dave, and I need to say this before we get started, one thing we do know is that it is highly likely that whoever is operating these UAPs, right, unidentified area phenomena, is most likely moving through a fifth-dimensional space, right? This is the only way that some of these things make sense, appearing, disappearing, being able to move seemingly through things. Because if you can move in a higher dimensional space, you're not moving through it, you're moving around it, but you're moving around it in a way that we cannot because we are stuck in 3 dimensions.
You kind
that's my point.
You kind of phase out of this dimension into a transitory dimension and then pop back in at the destination you want to go to. So you didn't actually travel through our space, but you kind of just slid out, like putting finger holes into a sheet of paper. You pull your finger out of one hole and put it into another. And that's kind of the best way to describe it, as a flatland view.
Yeah, look, and that's right. So we do know like some of the technological capabilities. Maybe they all have it. Maybe there's some different ways. We now actually are looking at we're looking at a hyperspace drive. We actually are.
They're talking about it, that it's they've created the concept is far easier than they thought initially, having to have something about, capturing a neutron star and having them, should be able to contain it somehow and use its mass. No, in fact, the torsion physics, Mackie, of spinning very lightweight things, right, around in a circle, creates a field, and that's what they've mathematically discovered just like last month.
Does that remind us of anything?
It does.
Anyone?
The LHC.
The bell, the Nazi bell, also.
Liquid mercury, the red mercury. Yep.
Red mercury, Victor Schauberger's physics. There's a whole.
Schauberger, yes. And the LHC is rapidly moving stuff in a circle, which causes a dip in the middle, the exact center point of it, causes a reality dip.
There's a whole branch of science, specifically in physics and astrophysics, that seemingly was abandoned. Clearly not abandoned, but just not no longer accessible to us in the mainstream, because it was just no one. The people that were studying it and making advances, they were working underground somewhere, right?
Yeah, that's what happens to people. You find something and then you just get vacuumed up by MIL.
What happened to Bob?
Who?
Bob.
Nothing.
We've got a problem here with Jimmy. He's talking about Bob.
Again.
Where's Jimmy? Who's Jimmy? So my point is that the science is progressing with or without us, and it exists. Look, we know that we don't understand the universe. We know it because there are things in it we have simply no explanation for. Spooky action at a distance. Quantum entanglement makes no sense. We don't understand it. We don't get it.
Entangling quantum tardigrades? What?
Yeah, exactly. And why would information, be transferred instantaneously? It doesn't make any sense. It makes no sense to us. But we know that we don't know how the universe works. Others might understand it better and maybe even fully.
And maybe in time, it'll become a thing that's disseminated to the bottom dwellers.
Where we are.
Bottom feeders.
And the information that we're going to impart on you now.
Yes, I love ocean scallops. Yes, absolutely.
we should. It's pretty easy to digest, and we're giving it to you because I want to be able to dispel the myth that it is impossible. Because that's the argument. Oh, it's impossible for ancient aliens to have come to this Earth, etc., etc. Now, I don't think you have to necessarily have ancient aliens to explain all the anomalies. I'm sure we had ancient technologies in the dim and distant past. I also believe that we were a spacefaring species that might very well have had contact with other species out in the galaxy, right? And then something happened, and now we don't. Maybe there was a solar war that destroyed the planet, that once inhabited the ecliptic that is now, or the orbit rather, that is now the asteroid belt.
That's right.
I mean, you look at the massive scar on Mars. That doesn't look good. Right, Venus is going around the wrong way, right? So there's a whole bunch of stuff in the solar system, the Moon, Earth I mean, we've spoken ad nauseum as well. There's a whole bunch of stuff that just doesn't make any sense, and we just don't think about it because it's too hard, or people say, don't think about it, please. Now, let's talk about the size of the universe. As far as we know it, it takes us around 3 days to reach the moon today, right? Thereabouts. It's approximately 7 months to get to the closest planet to us, which is Mars. About 7 months with our current technology. It takes about 15 months to reach Venus, 6 years to reach Jupiter, and 7 to reach Saturn, 8.5 years to reach Uranus. That's funny. 9.5 years to reach Pluto. It's the closest dwarf planet, and 12 years to get to Neptune, which is the farthest planet. Now, 200 years ago, right, it would take us years to circumnavigate the globe.
Mm-hmm.
It would take us months and years again to get to anywhere on the planet with the sailing ships that we had. So it is now technology has advanced and we've moved forward 200 years, and then now the same time span that it would have taken a European, for example, to go to let's say across the Pacific, or go around Cape Horn and then go into Asia and maybe cross the Pacific and go to America.
England to Australia by boat. Yeah.
That time span we could now reach Venus in. If you wanted to circumnavigate the globe and really explore it for 6 years or longer, that same time we could reach Jupiter. Right. So just to put it in context, we did do these journeys. We have done journeys like this. Right. Now, is it harder? Do you have to account for more eventualities? Do you have to bring a lot more provisions? The answer is yes. Yes, the problem is harder. The time frames, though, are not humanly impossible. Right. That's my point here. These time frames, they're achievable in a lifetime. So if a person could choose to go to, for example, Neptune, that's the furthest. It'll take 12 years to get there. And then 12 years to get back. And, they would have aged 24 years, right? So they might have left when they're 20. For argument's sake, they come back when they're 50, right? It is, but my point is it's achievable in a human lifespan. Now, let's look at the sun. The sun is 0.00001581 light years away. Best case scenario, we could reach it in 25 days. So how big is the universe, as far as we know? There's actually a couple of different
measurements,
opinions here, but it's about 93 billion light years big. Right? Now, how much is that? Well, let's think about the sun again for a second. The sun is 1 astronomical unit, AU, away from us. We call that an AU. It's just arbitrary. Distance Earth to sun, 1 AU. 1 AU is 149,598,000 kilometers, or roughly 93 billion miles. In our top shape, we could reach it in 25 days, right? 149 billion kilometers. Now, the universe is 93 billion light years across, we think. And just one light year is equivalent to 63,000 astronomical units. 63,000. As such, 1 light year is the equivalent to 9 trillion kilometers, or about 6 trillion miles. And our universe is 93 billion light years in diameter. That's pretty big. But that's not the end of it. Again, we don't know all of it. The 93 billion years is just the observable universe. Okay, that's the universe which we can currently see with our best instruments. The real universe, or the whole universe, might be bigger, or it might not even have a boundary. We don't know. I'm only talking about what we can actually observe today, or what we think we can observe. And it's a ball-shaped region of the universe, the observable universe, right? So that's what our best space-based telescopes can see, because the electromagnetic radiation from these objects has had time to reach the solar system and Earth since the beginning of the cosmological expansion. Again, these are theories. We think there may be 2 trillion galaxies in the observable universe. Now, that number was estimated in 2021 at only several hundred billion, based on data from New Horizons. Assuming the universe is isotropic, the distance to the edge of the observable universe is roughly the same in every direction. The meaning isotropic, it's expanding at the same rate in every direction, right? That is, the observable universe is a spherical region centered on the observer. Make sense? Every location in the universe has its own observable universe, which may or may not overlap with the one centered on Earth. So if you're in Alpha Centauri, then you are the center of the universe. If you're on Kepler 2b, then that's where you are. That's your center of the universe. According to calculations, the current core-moving distance, proper distance that is, which takes into account that the universe has expanded since the light was emitted to particles from which the cosmic microwave background radiation was emitted, which represents the radius of the visible universe, is about 14 billion parsecs. That's about 45.7 billion light years. While the core moving distance to the edge of the observed universe is about 14.3 billion parsecs, or about 46.6 billion light years, about 2% larger. The radius of the observed universe is therefore estimated to be about 46.5 billion light years, and its diameter about 28.5 gigaparsecs, which brings us to 93 billion light years, which equals 880 yottameters, which is a lot. We won't worry about how much that actually is. Using the critical density and the diameter of the observed universe, the total mass of the ordinary matter in the universe can be calculated about 1.5 times 10 to the power 53 kilograms. So, again, that's what we think at the moment. That's what we can see. That's the size of the universe. So my point here is it's very, very large indeed. Dave, why don't you tell me about the age of the universe?
I will, but first a quick comment. If you were to fly to Alpha Centauri today with our current technology, 10,000 years. 10,000. It's crazy amount of time. You think about how many generations that you'd have to sustain, or just go into stasis, right? Whatever. But if we launched today, and then say we launched in every 100 years from now, every single spacecraft that we launched would have a new technology and would be able to go faster. We would overtake the one that we launched this year every 100 years. In fact, every 100 years, we would overtake all the existing ships that are going in that direction to Alpha Centauri with every single new one. We would, for 10,000 years, we would end up just popping into existence there, waiting for them all to arrive, says current science. Thinking that if we just waited the 10,000 years, we could just go there.
Well, honestly,
I know it sounds preposterous that we should consider it like this, but it makes total sense.
Look, it does. It actually does make sense. I mean, well, why go now? We just wait. Well, I mean, again, yes.
We could time out, right?
Yes, but
our civilization could time out and not exist anymore, but it doesn't matter.
Yes, that is true.
Well, how come you didn't go, in Red Dwarf fashion? So you only scored 2%. Jeez, that's awful. Did you find this certain planet? No. How come you didn't do any of those things that you were supposed to do? I didn't think we could do it. I paraphrase all of that. Yeah, you watch the episode, it's very funny. Anyway, the age of the universe. How old is the universe? Is the big question. This is by Leah Crane. Scientists' best estimate is that the universe is about 13.8 billion years old. My interjection here is I completely disagree to all of these numbers. Anyway, we'll keep going. But like so many of the largest scale properties of the universe, we are not entirely sure about its age. There are two competing estimates based on two competing measurements of the expansion rate of the cosmos. Meaning it could be as young as 11.4 billion years old, or it could be 13.8. The easiest way to get at the age of the universe would be to find the oldest star and then work backwards with what we know about how stars are formed. However, finding the exact age of a star can be difficult. Some stars have even confused astronomers by appearing to be older than the universe itself. Yes, one was contestably older by, a couple of million years. That was it. It wasn't billions of years older. And they know that because they use pulsars who all emit exactly the same light frequency, and they can see how far away something is measured on the Doppler effect, which also I contest that as well. And they also say as the universe is expanding, we as humans actually increase in our size, imperceivably, because the observer would see it, but we don't. Just as if you were traveling fast in a spaceship at the speed of light, everything would appear normal to you, but an observer would see that you weren't nearly moving at all. All right, so instead of determining how old the universe is by the age of objects within it, we use the expansion of the cosmos itself, winding back that growth to the Big Bang, when all of the matter and energy that exists now exploded outwards from a minuscule point, or a singularity. The problem there is that the expansion of the universe is not constant. By looking at the movements of distant objects, we can tell that over time, the expansion has accelerated. In order to understand how the universe, how old it is, then we have to figure out the rate of that acceleration, which is represented by a number called the Hubble Constant. That's where the trouble comes in. There are two ways to measure the Hubble Constant. Oh boy, it's like philosophers talking about something on the television, and they have conflicting views. One uses cosmic microwave background, or the CMB, that's the radiation, 3K everywhere you can see, you can measure. A relic of this is believed to be a relic of the very first light to shine after the Big Bang. In fact, it's meant to be the explosion light wave that is moving away from us. As a sort of cosmic baby picture, we can take that light and use our models of the universe's evolution to calculate what it ought to look like now, which gives one measurement of the Hubble constant. Remember, everything we're seeing back in time. And so if you have to roll back that time, what did it look like? One other method, called the local measurement, is more simple. It uses observations of relatively nearby galaxies and supernovae to measure the rate of expansion of the universe and how that changes between those objects. But those two measurements, the baby picture and the recent one, disagree on how fast the expansion of the universe is accelerating. If the CMB measurements, the 3K, hold true, the universe is about 13.8 billion years old. If the local measurements do, it could be as young as about 11.4 billion years. Cosmologists around the world are chipping away at the problem, but so far there is no solution in sight. Ironically, only time will tell how old the cosmos really is.
And just on that, I mean, there's a few theories have emerged, well, a couple really, that state, well, there is actually, the universe has no age. Yeah. It is simply always there. It might contract, it might expand, but it is not, it doesn't have, there wasn't a Big Bang per se, which of course means that the CMB, the cosmic background microwave radiation there, is not really a good indicator of anything, right? And Dave has proposed an alternative theory, which explains red and blue shift in different terms.
So quite simply, we need instruments to measure different distances away from Earth. So visible light only carries so far, and then going upwards in the spectrum, actually downwards in the spectrum from visible light, we start to see further and further. Microwaves are less than visible light, and then radio signals are way, way, way down. And so using radio telescopes, we can see further. Now, ironically, if the Doppler shift isn't, if it's the only reason how they've become or arrived at all these measurements using Doppler shift, but really what the truth was that light just ages. And that's not a concern of anyone using the Doppler shift. They just say, no, it's constant, doesn't matter. Expand and shrink the universe and you get redshift, it doesn't matter. Something moving away goes red, something coming towards you is blue. That's Doppler effect. I know. I studied it. But then what I realized was the downshifting of the frequencies, the further something is away, to me indicates that they're wrong and that light actually downshifts in the EM spectrum. And therefore, that's why we can only see with certain instruments, certain things so far away, and it completely matches the EM spectrum the further something is away. Hang on, that makes more sense to me. And the only thing we're really seeing is time. We see time going back in time because it took time to get here. And this is the problem. So they've aged the universe in its size based on the Doppler effect, and it could be completely wrong. They could be so vastly wrong that they had to create, for all the explanations of the universe expanding, they had to create dark matter and antimatter.
And dark. Well, no. We know antimatter
dark
exists.
energy.
It's
dark energy as well.
Yeah.
So dark matter and dark energy, which was just something. Oh, it doesn't. It makes the equation work if I pop it in to the equation.
But we haven't seen it yet.
Well, no
dark
one's.
Energy, dark. No.
That's right. So no one's seen those things yet, and they're confabulations, I think. They
were necessary. Yeah, they were necessary for the theories to work.
For the theory to work, where mine doesn't require that. It's only the entropy of light.
I think you need to follow your physics professors or teachers' advice and
I have to try and prove it, mate. That's what
that's
he gave me. Yeah.
Gather the evidence, prove it, and then we might have a brand new cosmology. But look, it's actually leading in your direction because people or scientists are now saying, well, Big Bang, maybe not. Universe age, well, not really a thing per se, because the thing is this. Let me put it this way.
Mm-hmm.
The furthest we can see these days is, what did I say, 95 billion light years, something like that?
Mm-hmm.
Okay, that's the furthest we can see. Now, if you were to go to that place, 95 billion light years away, right? Just bear with me for a second.
I'll be tired.
Then their observable universe would also be the sphere. But the sphere would only reach in one direction to us, in the other direction
That's right.
Would reach 46 billion light years into another direction.
That's
completely.
Right. Mm-hmm.
So, it becomes really difficult to imagine the size of the universe because it might not be a finite construct. Okay,
yeah.
or at least not the way we understand finite. Now, by finite, I mean the Earth has got a finite surface, but there are no boundaries to it. You can walk around the Earth as much forever until the end of time. You can if you want to, because there are no boundaries. It doesn't end, but it is a finite construct.
Mm-hmm.
Whereas the universe per se, our universe, or maybe certainly the multiverse, is maybe not finite. Maybe it is truly infinite. That doesn't really mean anything to us because we can't conceptualize it. We don't really understand it. It's just bigger than what we know now, right? Mm-hmm. Same with the age of the thing. We don't know how old it really is. It doesn't make any sense. Like, we don't know. I mean, if this whole thing about the cosmic background radiation is wrong, because the assumption we start, okay, we're saying here, CMB is the first light that was created by the Big Bang. If there was no Big Bang, then the cosmic background or the cosmic microwave background radiation is not what we think it is.
That's right.
Make sense?
And what it could be is just the glow of the continuous expanse of the universe past what we can measure. If that could be just the remnant of what's past that vision. If you and I are standing exactly, say, let's just call it 100 miles, right, away from each other, and the air is maybe it's Southern California pollution air, right? We probably couldn't see each other. Right? Let's make it a kilometer or a mile. We'll make it 1 mile. You've landed in LAX, and we're standing exactly a mile from each other, and I can just make you out on my horizon. Can't see anything past you, but I can just make out where you are. But if I turn and look in the opposite direction, I can still see a mile away from me. You can see a mile away from you, and you can see me on the other extreme of that. Right? So together we can see 3 miles.
That's correct.
I can see my mile away from me, my mile to you, and you see a mile away from me again past you. So this is what we're trying to propose here as an argument. Yes, these are just spheres of visibility in which it is much bigger. And now we're not just making this up. This is something that's currently an idea. It's a topic going through science where they're going, well, we can only see this, but possibly it's going further. And then there's other arguments about there being a multiverse. But back to you in the studio, Mackie.
No, but again, So even if this universe were infinite, right? That doesn't mean the multiverse isn't either. I mean, every universe within the multiverse would equally be infinite. Now, something that doesn't really make sense to us, which is fine. It doesn't have to, because we are very limited in our understanding. Now, if you look at the quantum world, though, right? Now, these 95 billion light years is really nothing to an entangled particle. So if you move in a higher dimensional space, like in Flatland again, right? If you move in a higher dimensional space, it might as well be no distance at all, which it is. Exactly. It is no distance at all. So once we unlock travel in the fourth spatial dimension, or the fifth dimension in reference to our universe, being, time being the time dimension, the fourth dimension. So either any which way you want to slice it, I don't care. Once we have unlocked travel in that spatial dimension, 93 billion light years, one step, same thing, makes no difference.
Yeah, that's right.
And that's really the kicker here. And the thing is this: we really aren't that far away from it. We've started to unlock, or at least we've started to discover some of the fundamental principles here. Like again, like in the quantum realm, what quantum mechanics tells us, which makes no sense to us from an experiential point of view. So our universe that we experience has nothing to do with the reality of it.
No,
it's really important to understand it. Now, I think we have time for it. This is really the sort of the second last component here. And now we need to talk about the age. No, sorry, you just did that. And now we need to talk about, well, we've talked about the size of the universe. We've talked about the age of the universe. Now, we understand that roughly, right? It's a lot. It's a lot. My point in all of this was it's very big and it's quite old, right?
It's vast.
Really all I wanted to convey.
It's big, very big. Yeah.
It's very big. Now, there are two other points here that we need to make. And these are fairly recent articles. One is 2020 and the other one is, I think, 2022. So just this year. So how many Earth-like planets are there? I mean, if we're talking about, and this again, just for the doubters out there and for the debunkers, just to assume life has to be exactly like us, right? So they say, we only should consider Earth-like planets. Okay, we don't have to, but let's just to keep the peace, let's do that. So how many are there?
Morphize it. Let's do that then.
Bingo. Look, there may be as many, and this is from the article. The article here is how many Earth-like planets are there? As many. This is the subtitle here of the article. As many as 6 billion Earth-like planets in our galaxy.
Just our galaxy.
Our galaxy, according to the estimates. So that's from June 16, 2020, and the source is the University of British Columbia.
It's teeming with Earth-like planets. Yeah.
Right? Now, okay, so there may be as many as one Earth-like planet for every 5 Sun-like stars in the Milky Way galaxy. According to new estimates by the University of British Columbia astronomers using data from NASA's Kepler mission. To be considered Earth-like, the planet must be rocky, roughly Earth-sized and orbiting Sun-like, which is a G-type star. It is also to orbit in the habitable zone of its star. Again, our definition, right? The range of distances from a star in which a rocky planet could host liquid water.
It's actually water in 3 states is the definition, but that's fine.
Correct. But the point though is, I mean, the state of water depends on a variety of things. And the Goldilocks zone, in my opinion, is a complete misnomer. It's a fallacy. Because there's so many density of atmosphere,
that's
gravity,
correct.
Density of the planet,
so the magnetic field strength is also important.
Completely, absolutely.
Otherwise, all your atmosphere blows away.
Whoosh. No water. How's that? Now,
my water dish is empty.
UBC researcher Michelle Kunimoto, who is the co-author of the new study in the Astronomical Journal, says, my calculations place an upper limit of 0.1 Earth-like planets per G-type star, which is 1 in 5. Estimating how common different kinds of planets are around different stars can provide important constraints on planet formation and evolution theories, and help optimize future missions dedicated to finding exoplanets. According to UBC astronomer Jamie Matthews, and I'm quoting here, our Milky Way has as many as 400 billion stars, with 7% of them being G-type. That means less than 6 billion stars may have Earth-like planets in our galaxy. Previous estimates of the frequency of Earth-like planets range from roughly 0.02, potentially habitable planets per Sun-like star, to more than 1 per sun-like star, Dave?
Yes. Typically, planets like Earth are more likely to be missed by a planet search team than other types, as they are so small and orbit so far from their... No, it's actually so close to their stars. That means that a planet catalogue represents only a small subset of the planets that are actually in orbit around their stars searched. Kunimoto used a technique known as forward modelling to overcome these challenges. I started by simulating the full population of exoplanets around the stars Kepler searched, she explained. I marked each planet as detected or missed depending on how likely it was my planet search algorithm would have found them. Then I compared the detected planets to my actual catalogue of planets. If the simulation produced a close match, then the initial population was likely a good representation of the actual population of planets orbiting those stars. Kunimoto's research also shed more light on one of the most outstanding questions in exoplanet science today, the radius gap of planets. The radius gap demonstrates it is uncommon for planets with orbital periods less than 100 days to have a size between 1.5 to 2 times that of Earth. She found that the radius gap exists over a much narrower range of orbital periods than previously thought. Her observational results can provide constraints on planet evolution models that explain the radius gap's characteristics. Previously, Kunimoto searched archival data from 200,000 stars of NASA's Kepler mission. She discovered 17 new planets outside of the solar system, or exoplanets, in addition to recovering thousands of already known planets. An addition here, Mackie, was the planets that exist as rogue planets whose star went nova and they are just flying through space.
Yeah, no,
they've said there's at least 10,000 of those today that they know of.
There's some thoughts that Venus might be one of those, because, like I said, Venus is orbiting the wrong way.
Yeah,
we think that it might have been captured by
the
solar system at some point. Anyway, but so Dave and and I just explained to you that there might be 6 billion Earth-like planets in our galaxy.
Crazy numbers.
So point number one, the universe is quite large, right? Point number two, the universe is probably quite old. In fact, there may not be an age on it at all. It might be just very, very old, right? And second, thirdly, we have 6 billion Earth-like planets in our galaxy. Now, the next point we're going to make here is, well, all right, so how close are some of these exoplanets?
Good question.
To us. So we're going to take these one by one. Let's just start with the preamble here. So this is an article that was published January 20, 2022.
Oh, days today?
Yeah,
no, wait, a month ago.
Yeah, just a month ago, and it was from the from the website www.space.com. You can have a look at it yourself. A really cool website if you're interested in astrophysics. And Elizabeth Howell and Elisa Harvey published it. So scientists have found over 4,000 exoplanets. So these are actually the ones we found, not the ones that might exist, since the first such world was confirmed orbiting a sun-like star in 1995, according to NASA's exoplanet exploration page. More than half of these discoveries were made by NASA's Kepler Space Telescope, we just discussed this, which launched in 2009 on a mission to determine how common Earth-like planets are throughout the Milky Way galaxy. Discovering the first true alien Earth is a long-held dream of astronomers, and recent exoplanet discoveries have shown that small rocky worlds like our own are abundant in the galaxy. Again, we just discussed this. To qualify as potentially life-friendly, a planet must be a number of things, and we've discussed this as well. When telescope technology improves, other factors will be considered as well, such as the planet's atmospheric composition and how active its parent star is. And
they're starting to use that now, the composition of light, and breaking that up into what the composition is. They're able to tell now.
It's a spectral analysis that is it's really quite cool. It is really cool stuff. I mean, our instruments have become quite good. Now, so we're going to talk about. We're going to take these in turn. So the first one is Gliese 667 large c, small c. This exoplanet, which lies just 22 light years from Earth,
Wow.
is at least 4.5 times as massive as Earth, according to NASA's Jet Propulsion Laboratory. It completes one orbit around its host star in a mere 28 days, but that star is a red dwarf, considerably cooler than the Sun, so the exoplanet is thought to lie in the habitable zone. So it's cooler, but closer.
Yeah.
Getting that? Okay.
Mm-hmm.
However, the star, which was discovered with the European Southern Observatory's 3.6 meter telescope in Chile, may orbit close enough in to be baked by flares from the red dwarf.
Oh,
so
wow.
it's possible. So yeah, but anyway, so there's only
You would need a
22
huge
light years.
iron core with a huge magnetic field to survive it.
Quite possibly. If the life was like us, correct.
Well, yet anthropomorphizing it again. So Kepler 22b, it's one of my favorites. It lies 600 light years away. It was the first Kepler planet found in the habitable zone of its parent star, but the world is considerably larger than Earth, about 2.4 times our planet's size. It's unclear if this super-Earth planet is rocky, liquid, or gaseous. So Kepler's 22b's orbit of 290 days is pretty similar to Earth's 365, Space.com previously reported. The exoplanet orbits a G-class star like our Sun, but this star is smaller and colder than Earth's. Very interesting.
I know.
It's not the end of Kepler.
No, that's right. Now, this is Kepler 69c, and that's about 2,700 light years away. It's about 70% larger than Earth. So again, researchers are unsure about its composition. The planet completes one orbit every 242 days, making its position within its solar system comparable to that of Venus within hours. However, Kepler 69c's host star is about 80% as luminous as the Sun. So the planet appears to be in the habitable zone.
This is number 4, Kepler 62f. This planet is about 40% larger than Earth and orbits a star much cooler than our Sun, according to NASA. Its 267-day orbit, however, puts Kepler 62f squarely within the habitable zone, while Kepler 62 orbits closer to its red dwarf star than Earth does to the Sun. The star produces much less light. 62f lies about 1,200 light years away, and due to its large size, is within the range of potentially rocky planets that may hold oceans.
Kepler 186f. This planet is at most 10% larger than Earth, and it also appears to reside in the habitable zone of its star, though on the zone's outer edge. The planet receives just 1/3 of the energy from its star that Earth gets from the Sun. Kepler 186f's parent star is a red dwarf, so the alien world is not a true Earth twin. The planet lies about 500 light years from.
All right, number 6, Kepler 442b. This exoplanet is 33% larger than Earth and completes an orbit of its star every 112 days. According to NASA, the discovery of Kepler 442, situated 1,194 light years away from Earth, was announced in 2015. One study published in the Monthly Notices of the Royal Astronomical Society in 2021 found that this exoplanet may receive enough light to sustain a large biosphere. Researchers analysed the likelihood of different planets to be able to carry out photosynthesis. They found Kepler 442b receives sufficient radiation from its star. Nominal radiation, Mackie.
Absolutely. Kepler 452b. This world, whose discovery was announced in 2015, is the first near-Earth-sized planet that orbits around a star the size of the Sun. According to NASA, Kepler 452b is 60% larger than Earth, and its parent star, Kepler 452, is 10% larger than the Sun. Kepler 452 is very similar to our own Sun, and the exoplanet orbits the habitable zone. At 1.6 times the size of Earth, like we said earlier, Kepler 452b has a better than even chance of being rocky, its discoverers have said. Kepler 452b resides 1,400 light years from Earth. It takes Kepler 452b just 20 days longer to orbit its star than Earth does. So
wow, that's pretty
days.
cool.
That is pretty cool.
Yeah, number 8, Kepler 1649c. When the data from NASA's Kepler Space Telescope was reanalyzed, scientists discovered this one, Kepler 1649c. The exoplanet was found to be similar in size to Earth and orbiting its star in the habitable zone. During the initial data collection from the telescope, a computer algorithm misidentified the astronomical body. But in 2020, it was discovered to be a planet. It's located 300 light years from Earth and is only 1.06 times larger than it. So it's marginally bigger than Earth. Not even 10%. When comparing the light that the two planets receive from their stars, scientists found that this exoplanet received 75% of the light, the light that Earth does from our own sun. And it's 300, I already said 300 light years away.
Nice. Proxima Centauri B. Proxima Centauri. I was waiting for Proxima. I'm waiting for Alpha Centauri, but no Alpha Centauri, I'm afraid. Proxima Centauri B is located just 4 light years away from Earth. 4.24 light years, making it Earth's closest known exoplanet according to NASA exoplanet exploration. The exoplanet, which was discovered in 2016, has a mass that is 1.27 times that of Earth's. Although the exoplanet can be found in the habitable zone of its star, Proxima Centauri, it is exposed to extreme ultraviolet radiation. This is because it lies very close to its parent star and has an orbital period of just 11.2 days.
Whoa.
Like I said, that's pretty close. Only 4.24 light years.
I'm just going to cook tonight's dinner. I'm just going to put it outside. Oh, it's done. That's what it would. What about number 10, Trappist 1e? Orbiting the Trappist 1 are the most Earth-sized planets ever discovered in the habitable zone of a single star. This planetary system is made up of 7 worlds. It's 39.5 light years away from Earth. Water on most of these planets is likely to have evaporated early in the system's formation, says Space.com. However, in 2018, study found that some of these planets could hold more water than Earth's oceans. One of the worlds, called Trappist 1e, is thought to be the most likely to support life as we know it.
So, okay, let's just quickly recap. We've got a few more minutes. But the whole purpose of this was to show that the universe is big, the universe is old. The universe, in fact, our galaxy, holds potentially a multitude of Earth-like planets. And more to the point, we've just shared with you 10 of the most likely candidates that could hold Earth-like life, with Trappist 1e being the most likely, and it's only 39 light years away. In fact, one of them was only 4 light years away. Okay, so again, this is all about probabilities and the chance of something happening. Could we have been visited in the dim and distant past from people, creatures of one of these planets? Now the answer is yes, but it doesn't have to be one of these planets, of course, because there could be an infinite, well, not infinite, there's a host of potential planets in our galaxy alone that could host life like ours. But these 10 are really quite close. Well, not all of them, but a couple of them are quite close, and especially Trappist 1e.
Yeah.
Right. There's, in fact, there are even 7 planets in orbit, very similar to our solar system, for example, right? And now it seems that a recent study has found that that these planets could hold more water than Earth potentially.
So our solar system has 4 planets, and 3 of them more than likely had water. We still have it. Mars had it, it's proof. And the next one out might have actually been Earth's orbit before the collision with Tiamat. So that could be the remnants of a collision with Earth, because that's been theorized. So thinking about that, it could have been its own planet, or just never made a planet. That could have been 5 planets. Thinking about that in comparison to there being, that many in the Trappist, system, it's of 7 is a crazy thought that we could do that. Like it could have been a thing. If we were a civilization, Mickey, that left Earth in spaceships never to return, and we were never encountered anything bad, we could live for millions of years flying around.
Oh, completely. Yeah, absolutely. Now, so just want to make sure that everybody understands what we're saying here. It is not at all unlikely that a civilization might have happened upon us at some point.
Mm-hmm.
Or even that a civilization spawned here and went elsewhere.
Mm-hmm.
And nobody just asked the question in the chat. I just want to quickly go to that.
No, you won't.
What happens if we're alone in this infinite inorganic cauldron? Well, nobody will cross that bridge when we get to it.
Nobody. Very funny. All right, this has been another Dave and Mackey's Shiny Side Out, episode 518. We'll see you next week. And stay tuned for Dare Bear's awesome show, After Hours. Take care, everyone. See ya.